afternoon and welcome to the 2010 Science Fair at St. Thomas More School. Hands-on science is a characteristic of St. Thomas More School, and the Science Fair we're hosting today is a great example. The top scorers at our Science Fair today will go on to the regional fair, and every year St. Thomas More sends students on to state competition. Today with us we have Trevor Lind, who is presenting his Science Fair project for judging.
Have you ever accidentally shaken or dropped a can of carbonated soda? Well, I'm sure you know what happens when you open it. A big mess of Coke. I decided for Science Fair to study if there's an effective method to prevent this. First, I needed to understand why this happened. Soda is bottled under pressure in order to dissolve carbon dioxide into the liquid. This is done to give soda its fizz. The more pressure that is used and the cooler the liquid is, the more carbon dioxide that will dissolve. The carbonation is maintained by sealing the bottle or can at this high pressure. If the soda is not shaken, the gas at the top of the container expands, and you hear a hiss as it leaves the container, but no explosion. However, when the soda is shaken, small bubbles collect beneath the surface of the soda, where whirlpools decrease local pressure and gas comes out of the solution. Now, when the soda is opened, bubbles beneath the surface expand and push fluid out of the bottle, a soda explosion. Some possible interventions to stop this include tapping on the bottle in order to get the bubbles back to the top of the surface, or cooling or heating the can in order to dissolve the carbonation. I decided to test 4 interventions: tapping on the top of the can, tapping on the top of the bottle, tapping on the side of the bottle, cooling the bottle in a cool water bath, and heating the bottle in a hot water bath. I hypothesized that tapping the side of the bottle would be the most effective. Cooling the bottle and tapping on the top would also be effective, but heating the bottle would worsen the explosion. I got 25 12-ounce bottles of 7-Up in order to complete 5 trials of all 4 interventions in a control, which would have no intervention. For each trial, I took 5 bottles and shook them one at a time for 30 seconds. For 15 seconds, I applied one of the interventions. Exactly 15 seconds after the shaking, I would open the can and let it explode. I tried to open it as fast as I could. Afterwards, I would measure it and measure what was still left in it, and subtract that from the original 355 milliliters and see how much was lost. I averaged my results. The independent variables in this experiment are the interventions: tapping on the top of the bottle, tapping on the side, heating it, and cooling it. The control is the one that nothing was done to for the 15 seconds. The dependent variable was the amount of soda that exploded. The results for all 5 trials are recorded here. The average soda exploded for each intervention is recorded on this bar graph. My hypothesis was confirmed. The most effective method was tapping on the side of the bottle, where only 45.4 milliliters were lost, compared to the control, where 62.4 milliliters exploded on average. The cold water bath also was effective, which lost 52.4 milliliters on average, as was tapping on the top of the bottle, which lost 54.8 milliliters on average. Heating the bottle did, in fact, increase the explosion 70 milliliters on average. Of note, however, is the range of results for each trial is large. For example, when no intervention was applied, results ranged from only 32 to 85 milliliters lost on all 5 trials. Likewise, for tapping the side of the bottle, resulted in a range from only 5 to 75 milliliters. This suggests some unforeseen or confounding variables. Possible confounding variables include changes in room temperature during the 5 trials, differences in the way the soda was shaken, small differences in the time it took to open the can or bottle, time since bottling, or differences in bottling of the soda. Repeating the trials is done to balance out this unforeseen variables. It could be improved by doing it 10, 20, or even 100 more times. Some other questions for future trials include testing other brands of soda, testing other sizes of cans, testing soda at temperatures other than room temperature, and testing if a combination of variables may decrease the explosion, like does tapping on the top and the side is more effective than just tapping on the side alone. In conclusion, if you accidentally drop or shake a can of pop, you should tap on the side to most effectively get rid of the explosion.
Thank you, Trevor. That's a great project.